Hello and welcome to this presentation. Today I will talk about using a diffuse illumination for holographic OCT. So we started this work as Daniel Publitz von Zeiss came with an idea from a patent that he wrote about using a diffuse illumination for holoscopy. And we were also very inspired in the process by work from Adam de la Zada's group about speckle modulation to reduce speckle noise, and work from Oxorius and colleagues about using a multimode fiber to reduce multiple scattering in Fourier domain full field OCT. We have here studied the effect of the diffuse illumination in holographic OCT for speckle noise, multiple scattering, and spatial coherence noise. So what we understand by speckle noise is the effect that occurs when the roughness of the surface is larger than the wavelength. So if we consider 1 pixel, then we have light backscattered at different depth that is going to randomly interfere positively or destructively, which means that the intensity we detect from this pixel is different from the actual reflection coefficient of it. And in OCT, it happens all the time because the size of the voxel actually is much bigger than the wavelength. So then we always have speckle noise in OCT when we have biological tissues. And speckle noise is usually reduced either digitally by applying some form of smoothing, or with hardware by changing the speckle patterns and averaging different ones, so by changing the angle, the polarization, or the wavelength. And it should not be confused with multiple scattering noise. So in OCT we detect the depth at which light has been backscattered from the time delay. And when light is multiply scattered and it has a longer optical path length and time delay, then light is detected at a deeper depth than it was actually backscattered. So the consequence of that is that multiple scattering appears always below the sample, and the deeper we go, the more we have of it. And because it's a random process, then it also forms speckles. And multiple scattering is typically reduced by introducing some form of confocal detection. So with scanning OCT, the tip of the fiber acts as a confocal, but in full field OCT it can be used also with partial spatial incoherence. So either when spatial coherence is 1 pixel big, or even something like 50 pixel big, so that light must multiply scattered to the side goes outside the coherence area, so when it goes back to the camera it cannot interfere and is not detected. And that's why we get images here from Oxorius and colleagues where there is no multiple scattering and then there is no noise below the sample. And finally, we also studied spatial coherence noise. So in a simple case, here we considered 2 scatterers at Rayleigh's distance with at a slight different depth, so that they have a slight different phase shift. And if we try to resolve them with incoherent light, the intensities add up, the phase doesn't matter, and then we can always resolve them. But if we have coherent light, as we do in OCT, then it's not the intensities, but the complex amplitudes that add up, so that there is this random interference as well that make us not being able to systematically resolve the scatterers. They can only be resolved if the phase shift is favorable. And we call this spatial coherence noise, this unwanted interference between light from adjacent scatterers, and it also includes other effects like diffraction noise or ringing artifacts. And spatial coherence noise can be removed when spatial coherence matches the pixel size. So here is the setup that we used for this diffuse illumination holographic OCT. We had the conventional broad sweeper from Superlume and a fast camera at 60 kHz. And the particularity of the system was to use 4 beam splitters, so then we could have the diffuser introduced only on the object arm, so then it was diffusing the field that illuminated the sample, but only on the way to the sample. So the light from the sample to the camera did not go through the diffuser second time. We used a single or multimode fiber to see the effect of it, and sample, the diffuser was built by Zeiss so that its scattering angle was matching the detection angle. So then we have equal illumination and detection angle. So if we look in the foyer plane, so the pupil plane of the microscopy objective, the effect of it compared to the single or multi-mode fiber is that we should have with a single mode fiber only a tiny spot, which means that we are illuminating the sample from a single angle. And once we have the diffuse illumination, then suddenly this spot is largely broadened, and then we're illuminating the samples from a large variety of angles. So then it's no longer a uniform illumination as we would get with a single mode fiber, but kind of a speckled field. So to understand what's going on in the sample, on the other hand, it's nice to look at this schematic. So with the multi-mode fiber, we reproduce partial spatial incoherence. So we have these coherence areas that we project on the sample, but we also project now an intensity pattern with high spatial frequencies, and then we're just combining those two ways of structuring the illumination field. So coherence areas and this intensity pattern. To assess the effect of the diffuse illumination, it was only partly positioned on the optical path. So then we could look at the sample with half of the field of view being diffused and the other half of the field of view being a plane wave. And we saw different things with different samples. So then if we have something like ground glass where we have single scattering or reflection and we keep the phase peak static, then we see that the image is corrupted because we are projecting onto the sample an intensity pattern that hides the features of the sample. But when we have a sample that is already diffusing and there's multiple scattering, such as this one that is Teflon slightly below the surface, then we cannot even see the illumination pattern. So we don't see the difference between the diffuse and plane wave. Now, what we did was to keep the faceplate static during the recording of one volume, and then it was moved from one volume to the next. And when we translate the faceplate here and then we average 100 volumes, then we can see a clear improvement in the image quality. So there's the averaging of the intensity pattern that we project on the object, but there's also the averaging of the speckle noise. So when we have a close-up view on the sample, then we can see that there are some features that become much better visible. So here there is no increasing of the resolution in practice, but because you would get rid of speckle noise by applying a smoothing of the image, you would lose resolution. So by not having to apply this smoothing, then you still have a gain in resolution in a way. We combine this faceplate diffuse illumination with a multi-mode fiber to benefit from the advantage of both methods. So then with the diffuse illumination, we're reducing, smoothing the speckle noise, and with the multi-mode fiber, we are rejecting part of the multiply scattered light. So then we have an intensity profile at depth that shows less multiple scattering. And so when we look at these B-scans, we can see that we have a speckle noise that is smooth and less intensity because of multiply scattered light that is rejected by the spatial incoherence. So by combining these two, then we can benefit from the advantages of the two systems. Now the questions that made us think a lot was to which extent we could reduce speckle noise. Because if we represent what happens within a voxel and speckle noise in a very simple way, and we have scatterers with a different phase shift depending on the position, and then we have an oblique illumination, so we are changing the angle with which the scatterers are illuminated, then we're introducing a different phase shift, so we will have a different speckle realization. And once we have diffuse illumination with a given maximum angle, and then we are changing this diffuse illumination every volume, then we're wondering how many independent speckles can we obtain? Because if we want to efficiently reduce speckle noise, we need to have independent speckles to reduce them with the square of m low. And based on the literature, we expected a very modest gain. So then especially work from Weintraub and colleague indicated that there was only a very limited gain in SNR to gain by when the illumination NA is limited. So then there was only a gain of 1.3 or so. And also work from Stremplewski and colleague indicated for an optical situation that was very similar to ours, so then 4 element full field OCT, that they had a factor of less than 2 speckle noise reduction. So we expected something like this. But in practice, when we looked at our data, we saw something a little bit different. That if we look on the surface of the sample, then we have a gain that is kind of modest. But then if we look at depth here on the backside of the sample that we were imaging, then we had an improvement in speckle noise that was much bigger than a factor of 2. That was following the law of independent speckles. So like we could here obtain 100 independent speckles, which was much more than we expected. So then why did we get such a good speckle reduction? And our understanding of the situation is based on this differentiation of speckle, that there is the signal carrying speckle, that is light directly backscattered, for which we expect a limited speckle noise reduction. But there's also the signal degrading speckle, so the speckle from multiply scattered light. And for these, we do not expect that they are similarly bounded by the limitation in NA. So then at depth, we get better speckle noise reduction because we have more and more multiply scattered light. And for this, it's possible to decorrelate much more easily the speckle of multiply scattered light. So that's why the benefit of the diffuse illumination seems to be here to further reduce the influence of multiple scattering. So we checked that here with by imaging samples, by placing a diffuser on top of the sample to be in multiple scattering conditions to image the sample, and by imaging these samples with and without faceplate, so with and without diffuse illumination. And what we saw is that for this lens tissue here and for this USF target, in both cases, we could largely reduce the effect of multiple scattering. And for us, this is not really speckle noise reduction here, although there is partly speckle noise reduction for single scattered light, but it's speckle reduction of the multiply scattered light. The other thing that we studied was spatial coherence noise. So then, as said in the introduction, we have this problem of having 2 diffusers side by side at Rayleigh's distance, and then with coherent light, it's only not systematically resolved based on the phase. And what we have with this diffuse illumination is that we are making a coherent detection, but we are incoherently averaging different coherent detection. And when we write down the interference between these 2 scatterers, we have the intensity terms plus the sum of complex phases that with a phase difference between them that depends on the illumination. And the thing is that if the diffuse illumination has sufficiently high NA to project different phase on adjacent pixels, then we can have a random phase, and then we can have this term converge to 0, and then also systematically resolve the scatterers, so we can obtain the same contrast as we do with incoherent light. We checked that with USF targets. So USF target is particularly good to demonstrate this effect because things are on the same depth, so then the phase shift is unfavorable normally to resolve adjacent features. And we see here that when we add the faceplate, then there are some close features that we can now resolve, but there's also the effect of having some large features that become resolvable only with the diffuse illumination because of this suppression of this coherent artifacts is interference effects between structures due to the random phase. And for us, it is not really an increase in resolution because it's the maximum frequency, optical frequency that we detect from the sample remains the same. It's more a matter of changing the contrast of the image, which for some sample can be beneficial and for others not so much. Now at this point I mainly talked about the advantages of the method, right? That for the diffuse illumination and incoherent averaging, then we can reduce speckle noise, we can reduce the speckle of multiply scattered light and suppress spatial coherence noise. And the cost of that is that it slightly worsens the contrast of individual volumes, and it requires to average many volumes, like 100 or so, to get a factor of 10 in speckle reduction. For spatial incoherence that is caused by the multimode fiber, then we prevent multiply scattered light from interfering, which is a very nice feature because it just needs within one volume, it's already very efficient. But the limitation is that it degrades holographic refocusing. So the question is, to which extent a partially spatially incoherent light can be refocused? So if we have here a USF target and we image it with a single mode fiber, then light is coherent, we can easily refocus it and not lose anything. When we do the experiment with a multimode fiber and then we have partially spatially incoherent light, the question is, can we refocus the sample? And the answer is actually yes and no. That yes, we can refocus the optical frequencies that we manage to detect, but we cannot refocus those that we do not detect. And although it seems at first sight that the sample is nicely refocused and we do not lose anything, when we looked more closely, we see that we are starting to lose something in resolution. And here is the explanation that we're making interference between the object and the reference beam onto the cameras with limited spatial coherence, so we need the coherence areas to match on the camera. When we have a layer in focus, then the coherence area match, light is landing where it should, it interferes, is detected. But when we have a defocused layer, so in OCT our sample is thick, and it can be so thick that one layer is out of focus, and when we consider light coming from this layer, it can actually be so defocused that it is outside of its coherence areas on the camera. So it's outside of the coherence area of the reference beam and it's not interfering. And it can be because the defocus is too great, because the angle is so great then the defocus is more severe, or because the coherence area is also too small. So that is these three parameters here, the delta Z of defocus, the size of the coherence areas R, or the detection NA basically. And the problem here is that when we have a layer that is defocused, what we're going to lose first is the part of the light that is the highest detection NA. So then we're going to lose the part of light with that carries information about the highest resolution, because a greater angle means the higher spatial frequencies. And there is this compromise to realize between the defocus, so the thickness of the sample that we're able to image, the size of the coherence areas, so then in the ability to reject multiply scattered light, because smaller coherence areas mean better rejection of multiply scattered light, and the detection, so that is the lateral resolution. So we need to come to a trade-off between those three. And if we don't, then at depth we will lose resolution. And this should not depend on the illumination being diffused. So we check this experimentally. We image samples with a single mode fiber or with the multi-mode fiber with and without the diffuse illumination, and we check that with single mode fiber everything is coherent, and at depth we refocus the image and we don't lose anything. But with the multi-mode fiber, and we have a certain defocus of 0.25 or 0.50 that we refocus. So here the images have been refocused, when we looked at the images themselves or at the Fourier transform and of the complex hologram and look at the frequencies that we detect, we see that we're starting to lose more and more frequencies at depth, and that is true with or without diffusing illumination. But what we saw is that we could have, for our given detection and size of coherence areas, we could maintain a thickness that was relevant for the kind of sample that we're interested in. So plus or minus 25 millimeter, that gives a total thickness of 0.5 millimeter, could still be imaged with diffraction limited resolution, and that matches the formula that we obtained from geometrical optics that said that there was also a defocus of 0.22 that was acceptable. But there is another problem with the diffuse illumination, so it's more on the illumination side, not on the detection side, that we have a sample that has a certain thickness, and the pattern that we project on it has a certain depth of focus as well. And diffusing the illumination with large angles is going to make it much thinner, the depth over which the pattern that we project remains sharp. So it means that at a certain depth, then coherence areas are going to be blurred. And if coherence areas are blurred, and then we refocus them on the camera, it means that we are going to lose SNR. And that's what we checked experimentally. So we had a piece of paper illuminated with diffuse illumination or plane wave illumination, and we imaged it at 2 different depths, and then we checked how much intensity we were losing over depth, and then we could see that for a defocus of 1 millimeter we were losing something like 2 dB or so, which is very negligible compared to, well, the problem that we had with the detection in this. So then the additional loss of intensity caused by diffusing the illumination compared to non-diffusing the illumination, still with single mode fiber, multi-mode fiber, is largely acceptable. So in conclusion, we saw that with this diffuse illumination scheme, we could overall increase the image quality, make the contrast of the image kind of incoherent, so have images as if they were obtained with an incoherent light source, while still maintaining the advantages of a coherent detection. So then we can still benefit from the coherent gain, from the phase sensitivity, from the ability to do the refocusing, and etc. To go into the details, then we saw that we think for single scattering speckle, then we have probably only a factor of 2 or so, but for multiple scattering, because we have a lot of it, then it's very nice to be able to suppress it arbitrarily, it seems. For the resolution, in our case, we think from our perspective, there's no increase in resolution, just a change in contrast, but it's very beneficial. And when we combine it with the multi-mode fiber, then we can even further improve the quality of the image by well, combining the advantage of the diffuse illumination and the multi-mode fiber that prevents light from interfering, multiply scattered light from interfering. The price to pay is that the contrast of individual volumes is slightly decreased, and it does require to average many volumes to get the advantage. At this point, we did not use the setup on eye imaging yet, but we see several advantages to it for that. Is that first, one idea was that when we use the diffuse illumination, then we are broadening the size of the hotspot in front of the eye. So then we are decreasing by 3 orders of magnitude also the irradiance. So then we can spread the light over the entire pupil. So then we can make the system much safer and potentially send much power in the eye if we have the a light source that would be able to send such amount of power. It would be really nice in the eye to reduce speckle noise, especially in the cornea where we're not limited to illuminate the sample in terms of illumination name. And for the coherent, because there's a lot of multiply scattered light, then it would also be very nice to reduce the speckle there. The disadvantage that we see at this point is that for phase imaging, to follow the phase changes over time, it makes it more tricky, because if the eye is moving with respect to the illumination pattern, then over time each pixel is illuminated with a different phase, which means that when we're trying to track the phase changes intrinsic to the pixels, to the physiology of the eye, then we cannot distinguish what is due to the changing in illumination or changes in the intrinsic phase of the pixel. So to finish, I would like to thank my colleague for this work, and thank you for your attention.